My name is Bhavna Soman. I'm going to be talking about some work that my colleagues and I have been working on. I'm going to talk about something slightly different. I'm not talking about like a new ML-based method that we can apply to a security problem. I'm going to talk about evaluating machine learning models that we use in security. So this is my agenda. I'll start with talking about the challenges that we have in evaluation methods today. I'll introduce the method, Firenze. I'll talk about the key ideas. I'll give some practical examples and then finish with some results and limitations. So when I think about the challenges in like the current applications of machine learning and security, the thought that comes to me is that often when we have these models that have been proven in academic literature or in experimentation, when we train those models using production data and then we ship them to a customer, we often see unexpected false positives or false negatives. And that's really bad because security is a critical area of application of machine learning. And when we have these unexpected false positives or false negatives, that really is bad for customer trust. For example, if an ML-based AV engine detects a business critical file or blocks a business critical file, it's really disruptive, and you can get calls from the CTO to complain about that. So all of those are really bad. Similarly, false negatives are bad as well because like an attack really went through, and that's disruptive as well. So that kind of happens. But when we look into why, here are some reasons that we've come up with. The real world data distribution that we see in security data sets, it's really hard to represent that in a finite labeled amount of data. There is complexity in the universe, and also there's the concept drift where the definition of what is benign and malicious keeps changing, and I don't need to convince this audience of that. And then labels are noisy. I saw that there were several talks yesterday where everyone was like, yeah, labels are hard, and I was like, yes, that's what I'm going to talk about. So yeah, labels are hard to get. Even for something straightforward like file classification, you have this like large nebulous space of unwanted files, and which way you label them, it really depends on who you ask or what your goal is. Something like family classification, like if you want to distinguish between an emotet or a trick bot, you can really get into arguments between even reverse engineers to do that clearly. So basically, reliable ground truth is missing. So if I continue talking about file classification, the vast majority of files that I see in a customer environment on a given day, I won't have any labels for. So when my model is saying, okay, this is good or bad, there is no way for me to check that. And finally, the feedback isn't there. So in a traditional use case for machine learning, I might have something like A/B testing where I can ship two models and I can get this implicit customer feedback, and then based on that, decide which model is doing better. But in the cybersecurity space, you don't mostly get this type of feedback. Like on any given decision where my model is detecting something as good or bad, I'm not going to get that customer feedback. We only hear when things go really wrong, and by that time, it's kind of late. So how do we handle this today? Basically, we do a lot of manual analysis. Whenever like your ML or applied scientist has trained a model, then they might run it in a shadow mode or a replay mode for a while where, it's generating these findings, but they don't go to the customer, they go to a backend system, and then a researcher is basically analyzing them manually to make sure that there are no unexpected false positives or false negatives. There are a lot of limitations to this approach. Basically, it takes a lot of time and manual effort every time you want to do this. It uses a scarce security talent. Our security researchers are a precious resource, and we would rather have them solving like the more difficult problems. And then finally, it impacts our ability to innovate, right? Because this manual evaluation loop becomes sort of a bottleneck. And every time you want to make change to a model, you have to go through this process to make sure that it will perform adequately on the customer environment. So it really, it lengthens your innovation cycle, which is bad. So here I'll talk about like our method. And the first idea that I want to talk about is that of a marker. A marker is basically a weak signal that is cheap to obtain. It is based on domain expertise. So if I am a security researcher and I'm triaging a bunch of domains, I might have some intuitions based on my past experience that might tell me that, oh, if this happens, then that domain is likely suspicious versus something is benign. So it's based on domain expertise. and then it's cheap to obtain. So here I'm trying to like remove the manual work as far as possible. So my markers are always going to be things that I can write a function for and then automate afterwards, because I don't want to involve a security researcher all the time. And then this is going to be a weak signal. So all of these intuitions, they're going to be imperfect. They're not always going to be right, but that's okay, because the idea is that we're going to combine this information from multiple markers over populations to make decisions about a model, about the performance of a model. So that's how we're going to use these markers or weak signals. So I'm going to give a toy example here. So let's say I'm doing domain classification and I'm triaging a bunch of domains. I might say that, if a domain is new, it's likely bad. And this is kind of, a very characteristic type of marker, because it's not going to be always right. There are plenty of new domains that are perfectly benign, but also like if I'm triaging them, if I see a new domain in my traffic, I might be like, oh, that's suspicious. So that's an example of a marker. Here are a few more examples. So let's say domain age was 1. I might have like a popularity-based marker that says that, hey, if this domain appears on like a benign public list, like a Majestic Million or Alexa Top K, then I might say that it's likely benign. Again, we know that malicious domains do sneak on to these lists sometimes, but as a weak signal, it's pretty good. And then I might have another one like saying that let's say I have a list of known good registrars, and I say that, hey, if the domain is registered with one of these known good people, then it's probably fine. So you can see like here we define like these marker functions. Basically, like this is how we're going to automate this domain expertise kind of intuition. And the way we annotate is that the marker verdict MJ of S is basically, it says what the verdict for the jth marker is for sample S. And that can be one of 3 values. It can be -1 if the marker says the thing is benign. It can be 1 if it says it's malicious, and 0 if the marker abstains. Now, it's really important to let the marker abstain, because the opposite of a security researcher's intuition doesn't always translate into the opposite outcome. Okay, so now we have markers. Now we're going to talk about combining these markers for a single sample. So let's say we have 2 domains. One is a nice looking one like Amazon, and then another random looking one. The models might say different things about these domains, and we're not going to worry about that for now. But we can easily compute our 3 markers that we talked about for each of these domains. We can say, whether it's popular or not by saying whether it appears on my list. The registration I can check, and then I can also see what the domain age is. So here we see that Amazon would score more benign, and then the other random looking domain would score more malicious. The last column, the combined marker score, right now we're calculating that using majority voting. But overall, the intuition is that this combined marker score, if I look at 2 samples, SI and SJ, and then if the combined marker score for I is greater than that of J, then I is likely more malicious than J. So that's like a simple intuition that we're building here by combining these multiple marker signals. So this kind of emulates like how a human expert might build confidence. They might look at these multiple aspects of a domain, and then they might combine that to say, oh yeah, this is more likely to be malicious, or like I have a stronger signal now. And also, like, yeah, I mentioned majority voting, and that's a pretty naive and simple method. But our space actually has low signal density, so it works quite well. But of course, we can try more sophisticated methods in future work. Okay, so we talked about how we're going to combine markers for one sample. Now we're going to talk about combining this signal over sets of samples. And we're going to do something really simple. We're going to just calculate the average marker score for the set of samples. And the intuition here is that if we have 2 sets of samples, set 1 and set 2, then if the average marker score of set 1 is greater than the average marker score of set 2, then set 1 likely has more malicious samples than set 2. Okay, so now we're going to continue with our toy example, and I'm going to talk about how we're going to use this set comparison concept to comparatively evaluate ML models. So let's say that I have this common universe of domains. I have a model, let's call it the reference model, and I score all of my domains in the common universe with my reference model, and I take the top K malicious domains. So this is a toy example, so K is equal to 5. So I take the top 5 most malicious domains by the reference model. I do the same by the test model. So I have these 2 sets now. I'll call the first one the reference set, and I'll call the second one the test set. Now, different domains from the universe may appear in the top case set of the reference or the test model, and it doesn't matter. There may be an overlap, there may be a partial overlap, it doesn't matter, because what I'm simply going to do is I'm going to calculate the marker score for each sample that appears in these tests. And this marker score is basically what we've done before, majority voting of these three markers: age, popularity, and registrar. And then what we can do now is we can calculate the average marker score for each test. So now for the reference test, I have ZR, which is the average marker score for the top case samples by the reference set. And I have ZT, which is the average marker score for the top case samples by the test set. Now, going back to our earlier intuition, I can now say that, hey, if the average marker score of those samples in the test set is greater than those in the reference set, then the new model is better at finding malicious domains because it is putting more malicious domains in its top K test. So that's the toy example. But of course, in a real world scenario, you want to judge two models on more than just that. So we define a few different locally interesting regions or sets. And of course, I'll define like the three here that are the basics, but obviously it'll become clear that we can play around with this and define sets differently based on what we want to measure. So we have our reference model. Let's rank everything that the reference model scores in our universe from most malicious to least malicious. And then I can now define the K most malicious samples and the K most benign samples in this spectrum. I can do the same thing for the test set where I'll have the K most malicious samples and then the K most benign samples. Now, what I'm going to do is I'm going to compare the top K test of the reference model and the top K test of the benign model to see which model is better at finding malicious events. And then similarly, I can compare the bottom K of the reference with the bottom K of the test to see which model is better at finding benign samples. And then I want one more definition of regions to kind of do a holistic comparison across global ranks. So here's how I define this third kind of comparison set. Something we might see is that like a sample may be ranked more malicious by model 2 compared to model 1. And there might be other samples that are ranked less malicious or more benign from model 1 to model 2. So then I can define, again, some sets here where I can say the up movers are the K samples that have the most upward movement in rank from the test model to the reference model, and the down movers are the samples that have the most downward movement in rank from the reference to the test model. So again, the intuition here becomes that if the average marker score of the up movers is greater than that of the down movers, then the test model is moving more malicious samples to upper ranks and more benign samples to lower ranks, and therefore is doing better. So this is our third test, but we have this question, like anytime we measure the difference in these averages, is that difference significant, or can it occur just due to random chance? So this is where we bring in our hypothesis testing from statistics, and we overlay that to give more rigor to this. So basically, we can say that the average marker scores, they will follow a normal or a t-distribution. So we can apply like a two-sample or a paired statistical test. In our presentation, we use the Welsh test. So what we'll do is we can use the two sets. We have the averages and the variances, and we can compare the significance of their difference. So this is how we'll finally define the tests, the null hypotheses for each. So for the top K test, our null hypothesis will be that the reference model is actually better, so its average marker score is greater. For the bottom K test, we'll define that average marker score for the reference model is less because it's finding more benign samples in that region. And then similarly for the up movers, we'll say that the average of the up movers is less than the average of the down movers because our null hypothesis is that the reference model is better. And then we test each of these assumptions, and if the assertion is false and the p-value through our Welsh test is less than 0.05, then we can say that the test model is better. Now there are a few things to note here. You can get different answers for each of these tests. So we have been in situations where one model does not outright perform better or worse than the other. It may perform better at the top K, but worse at the bottom K. So it really gives you like a fine-grained view of what it's doing better or worse. And And it can give you like an indeterminate result, because if the p-value is not passing the significance threshold, then it's indeterminate, and that's a limitation. And that way, so you don't always get an answer that you're looking for, or a yes or no answer here. Okay, so now I'm going to talk about an example on malware classification, and here I bring in our favorite Ember dataset. We all know that it's a standard PE malware labeled dataset. We're going to train 2 models using this dataset. A neural network, adversarially robust neural network, was published in NeurIPS, and then we're going to train the tree model that was published in the original Ember paper. We're not innovating on the models here. These are stuff that have already been published. We're just going to talk about comparing them. Both of these models were trained on the Ember 2017 train samples, and then we did some testing on the Ember 2017 test samples, and these are the results. Basically, here we can see that, we can see that, the performance on traditional metrics doesn't vary that much. So if one of these models were in production, we don't have enough of a strong case to say that, hey, let's ship a new one and do more engineering work. Okay, so here I'll talk about how we evaluated this with Firenze, and I'll go a bit faster. So we evaluated it using the Ember 2018 dataset, which emulates kind of our future dataset. And then we use the unlabeled samples because we're trying to mimic a real world use case where we don't have labels for these samples. We used k is equal to 50. We designed 5 marker functions. I won't go into everything, but I'll give just like one example. So one of the markers we used was if a section name, if one of the section names in the file is .upx or a case variant of .upx, then the file is likely malicious. So obviously we know that benign files use UPX, but likely, if a file is using UPX, it's probably going to be malware. All right, so this is our result. Here we can see clearly that when we look at the average marker score for the top K and we compare the neural network model and the tree model, we see that the tree model has a much higher average marker score, which indicates that it has many more malicious files with marker scores in its top K set. And it passes the significance test as well. So here we can say with some certainty that the test model is doing better. And we can see the same result in the bottom can the movers test as well, where the test model does better. And then since Ember is a benchmark data set with all known labels, we are able to verify this in 2 different ways. First, we downloaded VT verdicts for the unlabeled samples, and we used the same heuristic that the Ember paper had used, where more than 40 is malicious and 0 or less is benign. And we ran these classifiers and tested the outcomes. And then also, we tested them on the 2018 training data set, which is the labeled part of it. And then again, we see that there is in both of these tests, we see that the significance of the improvement in the test model is very high, which verifies the results that we got using Firenze. Talking about limitations, first of all, this does not preclude the need for good training data. We're trying to get around the requirement of labels in evaluation, but obviously we need good labels to train good models. We rely on security experts to define good markers. So this is where we're continuing to rely on security experts. We don't allow overlaps between marker signals and those used as features, because right now we're still working on this problem where there might be a correlation between some features or the markers. So right now we're just enforcing that, hey, if a signal is being used as a feature, then we shouldn't use it as a marker. And also test sensitivity varies with different parameters. And we have a research paper alongside this, which has a bunch of simulations on synthetic data where we varied various parameters and see how the test performs. And so, for example, one of the things that we notice is that if the value of K is really small, then the test sensitivity lowers. So that's some stuff to keep in mind. And then also finally, this proves fitness for use by comparison. Like we're not able to say in an absolute sense, which model is better or worse. We're just saying that, hey, this is better than something that is already good enough. What we're working on now, we're testing new ways for marker aggregation. working on adapting this method to estimate performance of a single model. And then finally, we're formalizing explainability with markers. Like one of the side effects we found of these markers was that when something is going wrong or when a test is failing, we can look at the individual marker outcomes and figure out where the model might be going wrong or doing better or worse. So there is this notion of explainability that does come in, but we need to formalize that. That's it, and I'm open for questions. Thank you so much.